All right, let's talk about work and power. Now, work we can define as the change in energy of a system as a result of a force acting over some distance. Now, we'll get back to the energy portion of that definition here in probably the next lecture when we talk about energy. Um, but keep in mind, if you're looking at the equation for work, work is equal to a force acting over a distance times the cosine of the angle um, between the force vector and your displacement vector. Um, so if you look at your equation there, right? If you've got a great force, you've got more work done. If you've got a great distance, you got more work done. Now, force is going to be measured in the unit of joules, and again, we'll talk about that more when we get to energy. Um, but one thing we do always want to take a look at when talking about the work equation is this cosine theta. So theta, the angle here, is a very particular angle, right? It's going to be the angle of difference between your force vector and your displacement vector. So take for instance, let's say you've got a force acting over a distance, right? And they're both directed the same direction, right? So the force vector is to the right, the displacement vector is to the right as well. Well, the angle of difference between those two vectors is 0 degrees, right? There's no difference in angle between those two vectors. And so if you look at the cosine of 0 degrees, well, the cosine of 0 is 1, right? So in this case, you've got positive work being done on the object. And so the fact that we're talking about work being positive or negative means that work, by definition, is a vector quantity since both force and displacement are vector quantities. So let's take a different example now. You've got a force acting to the right, and the displacement is to the left. Well, what kind of scenario could that be? Well, it could be a car coming to a stop or a baseball player sliding into second base, right? So it's a force that is slowing the object down. Well, in this case, the angle of difference between these two vectors is 180 degrees, right? They're pointed opposite directions. Now, if we look at the cosine of 180, well, the cosine of 180 is negative 1, right? So in this case, you've got negative work being done. Now, some component of your force vector must exist in the same dimension as the displacement vector in order for work to be done. So let's say, for instance, we've got ourselves a force that is, say, directed upwards in the vertical, and you've got yourself a displacement that's to the right. Well, the angle of difference between these two vectors is 90 degrees. Well, what's the cosine of 90? Well, the cosine of 90 is 0. So in this case, no work is done by this force here, right? Because no component of that vertical force exists within this horizontal displacement. So a good example of that would be, let's say you're a waiter, right? And you're holding a tray like this. Well, the force of your hand on the tray is directed upwards, but the tray is being displaced across the restaurant in a horizontal direction, right? So in that case, from a physics perspective, you've done no work. So again, you always want to be careful with that cosine theta. That theta is a very particular angle. It's that angle of difference between your force vector and your displacement vector. Now, one thing you also always want to look at as we progress through the year is combining equations. So if we know that work is a force acting over a distance, and we'll just say that positive work is being done here, we'll ignore the cosine theta for now. Well, what's force? Well, force is a mass that experiences an acceleration, right? So you can always derive an equation for work that involves mass, acceleration, and a displacement. And this equation comes in fairly handy quite a bit. So you always want to get used to being able to sub in old formulas into new ones. So let's take a look at an example. For some reason, the examples are backwards in the notes. So we'll start with example 10.1. That is work done in pushing a crate. So in example 10.1, Sarah pushes a heavy crate 3 meters along the floor at a constant speed. She pushes with a constant horizontal force of magnitude 70 newtons. How much work does Sarah do on the crate? Well, if we look at setting this up, right, so we've got ourselves a crate, and she pushes it for a displacement of 3 meters, and we know that she's pushing on it with a force of 70 newtons. And we want to know the amount of work that Sarah does. Well, again, work is force distance times the cosine of the angle between those two vectors. Well, in this case, theta, our angle there, is 0 degrees. Right, so the work would be 70 newtons times 3 meters times the cosine of 0, which is 1. So the work done there is 210 joules. So let's take a look at a little more complicated example. So in example 10.2, titled Work Done in Pulling a Suitcase, we're told that a strap inclined upward at a 45-degree angle pulls a suitcase through the airport. The tension in the strap is 20 newtons. How much work does the tension do if the suitcase is pulled 100 meters at a constant speed? So again, always start with just a basic little free body here. We got our force of 20 newtons, right? That tension force. It's displaced a distance of 100 meters. And we know that theta is 45 degrees. So again, we look at work being equal to force times distance times the cosine of your angle. So the work is 20 newtons times 100 meters times the cosine of 45. And we get the amount of work done by the tension force as 1,414 joules. Now again, be careful, especially if you're in pre-cal, that your calculator is set in degrees and not radians. And also one thing to consider here when we're looking at work, right, is that there can be multiple different forces doing work on the same object. So if we go back to that, well, let's look at example 10.1 again. Sarah's pushing a heavy crate across the floor. Well, we calculated that she did 210 joules of work. Now, if this is a floor that is not frictionless, well, there would also be work done by a frictional force, right? So there can be multiple different forces all doing work on the same object, right? And the combination of all of those forces would be what we call your network, right? So the combination of, if we're talking about Sarah pushing the crate across the floor, well, the combination of the work that she does pushing on the crate and the work done by friction opposing the motion of the crate, those two would combine into an overall network. All right. So let's take a look at example 10.3. So you've got a drag racer that is being slowed down by a parachute, and we want to know the side of the work done. So pause the video, take a second, see if you can't figure that out. Alright, so if you're looking at that drag racer, the drag racer has some forward displacement. Well, the parachute is exerting a force opposite that displacement, right? It's slowing it down. So in this case, if we're talking about the sign of the work done here, well, the work done would be negative work. So let's take a look at stop to think 10.2. We're given 3 different scenarios, and we want to know which force does the most work. The 10 Newton force, the 8 Newton force, or the 6 Newton force. So go ahead, pause that, and see if you can't figure it out. Alright, so the key here is we know that the displacement for all of these is the same, right? So if all of these undergo the same displacement, what we really need to be looking at is how much of the force in each one of these scenarios exists in the same dimension as your displacement, right? Whichever one has the greatest amount of force existing in that horizontal dimension will experience the most amount of work done on it by that force. So if you look at example, or the first one here, the 10 Newton force. Well, the 10 Newton force is a vertical force. None of it exists within that horizontal dimension, so that 10 Newton force does 0 work, right? No work is done by that 10 Newton force. Now, in the second one, we've got an 8 Newton force that is being exerted at a 60-degree angle, right? So if you take 8 newtons times the cosine of 60, you get 4 newtons worth of force that exists within that horizontal dimension, right? So if we were to break that force down, right, you'd have an 8 Newton force. Right, this is an angle of 60, and only this amount of force, right, the force existing in the horizontal, contributes or does any work, right? So only this component does work on that object. And so this component would be 8 times the cosine of 60, which gives you 4. Now that last scenario, you've got a 6 Newton force that exists fully within the horizontal dimension, right? So if we were to rank these, and we'll call this 1, 2, 3, right? It'd be 3 is greater than 2 is greater than 1. Now, notice that at no point in our discussion of work did we mention time, right? Because work is time independent. So let's say that there were 2 people, Bob and Dave. And Bob and Dave are both pushing the same crate the same distance. Now, they're going to exert equal amounts of force over the same distance, so they're going to exert the same work on that crate. Now, let's just say, though, that Bob is a little lazier than Dave, and Bob takes frequent breaks. And so Dave finishes the task in, say, 30 seconds, and Bob finishes the task in 2 hours. Well, have they done equal amounts of work? Yes. But where time comes into play is when we talk about power. So power is how much work can be done over a certain time period. So power by definition, right, is work over time. Or if we want to derive that a little further, if power is work over time, well, work is a force acting over a distance. Well, what's distance over time? Well, it's velocity, right? So you can always derive your equations further, right? So power is how much work is done in a certain time period. It's going to be measured in watts. And when you're talking about power, that's something that you see pop up a ton in your daily life. Like, let's say you're watching football, and there's always a billion truck commercials. Well, what are they always talking about? They're talking about the horsepower of that truck, right? So what they're literally telling you is how much work can be done by that truck in how much time, right? So a truck with a high power rating can do a ton of work in a tiny amount of time. And so you might see this conversion pop up. You don't really need it. It would never be on a test or anything, so you'd never have to memorize it, but it doesn't hurt to have the horsepower to watt conversion ratio just in case, right? And so 1 horsepower is 746 watts. So let's say that we've got 4 students. They run up the stairs in the time shown, rank in order from largest to smallest their power outputs, power A through power D. Now, before I tell you to pause it and try to figure it out, one thing you've got to keep in mind is that the overall displacement we're dealing with here is a vertical displacement, right? So all we care about is a vertical force. Now, if let's say you've got yourself an 80 kilogram dude and he's being displaced, say 10 meters, like in scenario A, well, the amount of force required at minimum for him to be ascended by 10 meters in the vertical has got to be just a tiny, tiny, tiny bit bigger than his actual weight, right? So if you do 80 times 9.8, well, you get a weight of 784 newtons. So at the very minimum, the amount of force he needs to apply is 784 point, a billion zeros and then 1. So we can always just round that up or down to 784 newtons. Right, so with that in mind, see if you can't rank these guys' power output A through D. All right, so let's go ahead and look at that. So in scenario A, we already kind of talked about it just a second ago. Right, you've got a force of 784 newtons acting over a displacement of 10 meters. The angle of difference between your displacement vector and your force vector is 0, and it occurs over 10 seconds. So you can calculate your work out to 7,840 joules. Work over time is power, right? So you take your work, divide by 10 seconds, and you get a power output of 784 watts. Now you do the same thing in B. Same force, same distance, just in this case, you have 8 seconds time. So calculate that out, you get 980 watts. Part C, the only difference here between B and C is that you have someone with a lower mass. Since they have a lower mass, they have a lower minimum force that would be required to cause them to raise themselves vertically. So you do your math, find work, find power, right? Work over 8 seconds, and you get 784 watts. Now in part D, you've got a guy that's going 20 meters instead of 10, right? It happens in a time of 25 seconds. We know that angle of difference between your displacement and your force vector is still 0. Calculate out your work, put your work over your time to find your power, and you get 627.2 watts. Right, so if we're going to rank this, right, B is greater than A equals C, which is greater than D. Now I'll be uploading some basic work and power questions. For the most part, they're pretty straightforward. And then the next video lecture we'll do is going to be on energy. Now the nice thing is the College Board threw out a few units from AP1 um, from this year going forward. So we actually have a lot of time to spend on energy, which a lot of people struggle with. So the good thing is that we're going to have probably about 2 weeks easily extra time to work on this. Um, but yeah, hope all is going well, and I'll talk to y'all soon.